Okay, no problem. I forgot to record the first part, but I will continue. I will try to record it later on. Okay? Because the first part was trimmed from the record. I forgot to record it, but now it's recording. Okay? So the first part I will try to record it separately, so you can revisit it if you want to. Okay? Okay. So now we are talking about the complexities for each operation. We will do enter how many times? 3 times. What about extract minimum? 3 times. Also, what about updating? 3 times. That's right? Okay. So the total complexity is V multiplied by the enter complexity plus V multiplied by the extract complexity plus E multiplied by the update complexity. Did you got it? Okay. But it depends, insert and the extract minimum and the update is unknown to now because they are specified or determined based on the data structure. It differs from that structure to another. So what if I'm using normal array? How to insert in a normal array?
That's order.
What's the order? Order 1. Array of 0 equals 1. Array of 0 and 0 equals something. I'm only indexing to enter, that's right? I'm saying A of 0 equals 1, or A of 0, 0 equals something. So in order to insert in an array, it's order 1. What about the extract minimum? How to extract a minimum from an array? I need to look over the whole vertices, which is order.
You have to check all the vertices.
Yeah, I need to iterate over all the vertices until I reach. I cannot reach the minimum until I loop over all the vertices and get the minimum distance. So it's order V. I will do it how many times? 3 times. V by V is V squared. So it's V squared. What about the update?
It's not all the time that you update. You only update.
Updating in an array. I need to update like ABC. What should I do? Array of 3 equals something.
Yeah, so order 1.
Updating is only order 1. So it's order 1. I'm doing it, sorry, E times, so it will be E by 1, which is E. So the complexity is E at the end. Is there any problem till now? You have any question? Okay, what about the probability queue? Before going to the probability queue, what's the total complexity here? Can you tell me? What's the complexity here?
That would be inside is plus, so it will be an addition.
It will be V square or V square plus E?
V square plus E.
No, V square only. What's the maximum number of E? What's the maximum number of E? What's the maximum number of edges in the graph? Each vertex is connected to every other vertex. This is the maximum number of edges, right? Which is V square. If I'm connecting the first vertex to all other vertices, it will have V minus 1 connections. And the same applies for the second vertex. And the last vertex, it will be V multiplied by V minus 1, which is V squared. So it will not exceed V squared. Yeah. So here, it will be V squared. Did you get it? What was the probability queue? Probability queue called something, uses something called max heap or minimum heap. I will tell you what's the purpose of max heap or minimum heap fast. The max heap stores here the maximum element, and here
the next
smaller, and here smaller. So each root follows some nodes which are smaller, because the root is the maximum. So the next level is smaller. The third level is smaller. Yeah. Minimum here is the opposite. This is the minimum, and those are greater. And this one should be smaller than those, because those are greater, and so on. Okay. So in order to insert or extract or update in a heap, either max heap or minimum heap, it's log. Okay. And this is very important. You should go through the max heap and minimum heap through YouTube. It's very easy. But you don't have much time to discuss it for today, so you can discover it on your own. But it's very easy. Okay? You have any question till now? So what's the complexity here? A log V. Okay, Fibonacci is different somehow. It inserts in order 1 and updates in order 1, but تعملها in order log v. So what's the best structure you can be used? Or depends. Or depends. No, Fibonacci is better. Here there is no log, and here there is no log. Somehow better. Not better because they are almost close, but it depends on what. What if my graph is dense?
Then there is.
It means that there are almost connections from every vertex to every other vertex. So E will be equal to what? V square. So here it's V square log V, which is much worse than V square. And here it will be V log V plus V plus V square. So it will be similar to this, but the array like reduces some overhead because of its simplicity when using it as a data structure. Okay? So if it's dense, the best is array. While it is sparse, better to go with probability Q or Fibonacci. Did you got it? You have any question? Okay, so Dijkstra, for like summarization, Dijkstra is very, very efficient in getting the shortest path starting from a single source to any other vertex in the graph. Okay, but the disadvantages for it is it cannot always work correct with negative edges. It doesn't handle negative edges correctly. So if I have negative edges, I cannot rely on Dijkstra. I should use another alternative like Bellman-Fodor. Bellman-Fodor works great for negative edges. Can also preserve or get the minimum bar, shortest bar. Okay? You have any question till now? Is it clear, or you have any question? Is there any question till now? For sure? Okay, let's begin our example because they somehow know. What's the clock now? How much is the clock? Good. Yeah. Okay, we don't need the more working. So now the complex for Dijkstra, we're using various Q or heaps for general, it will be E log V. We set V square for array, E log V for various Q. Fibonacci is D log V plus E. Okay, so we took the various Q because it's the most popular implementation, which is E log. Okay, we have some properties as we discussed the previous time, which are those four. Okay, so when we solve the two problems that we have, we will state the properties for each we will state the answer for each property. Okay. Okay, the first problem is called undergains. Okay. The problem is somehow like long, so you can tell me if you don't understand any small parts, you can tell me because they are very, very important. The idea behind those problems is very important. Okay, so please focus with me, and if you have any question, tell me. Okay, or interrupt me when I'm discussing it, so I can revisit it again. Okay. Is that writing clear, or I should make it bigger?
No, that's all.
Is it clear?
Yeah, it's okay.
At least in handwriting is small for me because, in order to be clear in the recording. At least is a rebel is by who has been assigned to go on an exploration. Mission to the mansion of the dictator. relevant to limit exposure, she decided to travel where underground okay. The first thing he's saying for you that there is some girl called Agnes, or some character called Agnes, some person which is a rebellious boy, which is a spy, who has been assigned, had a task to go on for an exploration mission, had a task to explore the mansion of the dictator President Ray. There was some president in the country that they wanted to explore his mansion. Mansion like a big house, right? Mansion. In Arabic it's called Asr, but I don't know in English it's mansion. Asr in Arabic. In English it's mansion. Okay, she decided to travel via underground sewer network to limit exposure. So in order not to be catched, she traveled via sewer network, which is the water under the ground. Okay? Okay. What are the characteristics of this sewer network? We told you that this sewer network, or this sewer map, first has n bidirectional pipes connected at junctions. Okay. First, it has n bidirectional pipes connected at junctions. What are pipes and junctions? Pipes? Yeah, exactly. But first, what is pipes? Pipes?
Those are the edges.
Are the edges, right? We can imagine that this is the pipe. This is the pipe. And this is the pipe also. What is this? This is called a junction. The junction is something that maps two pipes. Okay? So if I have this is a pipe and this is a pipe, where is the junction? It's this point, which connects those two pipes, which is considered here the edge. Yeah, exactly, like this point. So it's called here the vertex is the junction, while the pipe are the edges. Okay, he told you that we have n bidirectional pipes. So the pipes here, the edge is directed or undirected? Does it have a specific direction, or it goes either way? Bidirectional means it can go both ways. It can go from S to T or from T to S, from both ways. So it can be considered as the undirected. Is there any problem till now? Okay. What is the first thing? The second thing? The second thing, he told you that each junction at most connects 4 pipes. So each junction, each vertex has at most how many pipes that pass through this junction? At most 4 pipes. So 4 pipes, it means that it is sparse or dense. The graph here is sparse or dense.
Depending on the.
Why dense?
It connects to. No, it's not n. It's fast.
You have at most 4 pipes. So the junction is like n. You have only 4 pipes. So I will tell you what is the problem if you if you specified it or if you considered it as dense. Dense requires, which is better for dense? Array or variety Q and heap? Fibonacci heap. Array is better, right? If n, we always assume that n is a very large number. We are assuming that when n increases, what happens? That's right. So we cannot assume that n is 4, so we can say dense. If I make this, it will work very good for 4. But what if I give you another example or another input when n is 1 billion or 1 million, and in order to store an array 1 million by 1 million, it's impossible to compute it. So instead I will store only in an adjacency list or something like that, which will be very acceptable because it's million by 4, which is very small. Instead of 2 million by million, which is 10 power 12. That's right? So it's definitely sparse than dense. Because it's some constant. Even if the constant is 100, it's sparse. Because I'm saying when n increases, n is very, very big. It doesn't matter when n is small, because I cannot control n. N is a dynamic number. It can increase till very, very large numbers. That's right? Okay. He tells you also that every junction is reachable from every other junction.
That means it's connected.
It's also considered sparse. Okay. It means it's connected or disconnected.
Connected.
Every junction is reachable from any other junction. So beginning from any junction, I can reach any other junction, which means that it is
Connected.
connected. Is there any problem till now? Each byte is weighted with its each one is weighted with its length. Means so if this, which byte is larger, this byte or this byte? The horizontal byte is bigger, in fact, it will have a huge, bigger length, which is considered weighted. Because depending on the length of the byte, it has a huge or a bigger weight. So it's weighted. Okay, we have now determined what the properties. That's right. Okay, let's continue. I told you there exists junctions with motion Atlas doesn't know the sensitivity of okay. What is required in order of n log n? Find a path from entrance junction to the junction that maximizes distance to okay. The problem is telling you that each byte is weighted with its length, so it's weight. Okay? He tells you also that there exist junctions with motion sensors. There are some junctions that includes motion sensor within the junction. So this motion sensor determines or like knows when there is some motion beside it, right? And now this boy wants to go from the junction of his house to the junction of the mansion of the president, that's right? Okay. So he wants to find in n log n a path from the entrance junction, which we will begin from it, to the mansion junction that maximizes the distance to sensors. Why? In order to minimize the probability of being captured. That's right? He needs to minimize the probability of being catched. So we need to maximize the distance from those sensors. Okay. This is very important. First, we need to decide the vertices and edges. What's the number of vertices? The number of edges is n. And he told you that the pipes junction connects how many pipes? 4 pipes at maximum. So the vertices is smaller than the edges. If the edges is n, how much are the vertices in the graph? He told you that exactly each pipe has each junction connects exactly 4 pipes. And the pipes is n, it will be n over 4. That's right. He told you that at most it connects 4. You can connect 4 or less. So the vertices should be bounded by, should be greater. Sorry, smaller than n and greater than n over 4. That's right. Because if he told you that each junction has only 1 pipe, it will be n. If he told you that each junction has 4 pipes and the pipes is n, so it will be n over 4. He told you that at most 4, so it will be between both ranges. That's right?
Yeah.
Have you got it? Now we got the n and v. The v will be between those, which is order n, and the e will be order n. Okay, is there any problem till now? Okay. He tells you another piece of information that the sensor's radius is unknown. So others don't know how much does those sensors sense. What is the radius? It doesn't know the radius. What the sensor sense within. It is unknown. And also it tells you that those sensors are like made or are manufactured in different companies. So maybe some sensors sense in a different radius than other sensors. Each sensor may have different radius. Okay. What is the purpose here? The purpose is to find a path from the entrance junction to the maximum junction, but while maximizing the probability, while maximizing the distance, or in other terms, minimizing the probability of being captured, or being detected. How to do that? Can you think about it?
Do we know exactly which junctions have the nodes?
Which junctions have what?
The junctions that have the motion sensor. Do we know them exactly?
Yeah, I will give you an example now so you can understand it better. Imagine with me that the CO network looks like this. I have summarized the problem itself in some notes because the problem itself, that sketch of the problem is much larger than this. Somehow huge, so I only extracted out the most important points. Here is the entrance junction. Okay, here is the entrance junction. Okay, and the CO network looks like this. I have here, those are pipes, and this is junction. Okay, so here I can have what is this? This is the Mansion. Is it enrolled now? So here is the CO network. It consists of junctions, which are those vertices that connect different pipes, and those pipes, and also it consists of motion sensors. Some junctions have motion sensors. So let's imagine that this junction has motion sensor, and this junction also has. Okay. So how can I avoid the possibility of being catched as much as possible? I need to maximize the distance for those sensors, but maximize which distance? The distance to any sensor or the distance for the nearest sensor? Again, when I'm here, I'm trying to go away from this sensor or from this sensor?
From the nearest one.
From the nearest one. So at each point, I am trying to avoid the nearest sensor because the nearest sensor has a high probability of catching me, unlike the further sensor. That's right. So at each point, I try to find out how to find a pathway. I'm certain that I will do this mission, but when doing it, I need to minimize the possibility of being captured.
So you have to check.
Yeah, so I have to check what is the maximum distance that should I go through in order to visit or in order to reach the mansion junction, but while minimizing the possibility of being captured.
As you check
So what should I do?
As you check for the minimum distance, you should also, once you check the minimum distance, you should guarantee that it doesn't lead you to a motion sensor. What do you call it? Vertices.
What?
If you're looking for, like, let's say we check, right? We check if the distance or if the current ways that lead you to certain vertices, right? When we are checking, when we are trying to relax the vertices.
Yeah.
It's before you relax certain vertices, or before you check the minimum of those two vertices, you have to check if that vertices leads you to a motion sensor.
Yeah, but what if it leads you? What if it leads you?
And it is the minimum, you don't take it.
Yeah, but how can you guarantee? What if, like, here, what should you do? You should go up or go left or go right? Sorry, you don't know. But maybe if you go right, you find the motion sensor here. If you go up, you find. So you don't know.
So we don't know exactly where the motion sensors are.
No, we don't know. We have many motion sensors. Imagine a graph having like 1,000 motion sensors. You know where are the motion sensors, but what should you do? Will you go this way or this way? Go this way because you are avoiding this motion sensor can take you to another
Motion sensor.
sensor. You don't know. How can you think about it?
It's like if you set it traverse to go.
What? Yeah, what will you mark? Will you mark there is a motion sensor or not? But what is the benefit for this? You don't know how much does this sensor sense or what's the radius for this sensor. Also, you don't know how to. What should you do? You need to maximize the distance of being maximize distance when you go from S to T.
Okay, so you're taking the larger distance, not the small distance.
No, but taking the longest distance means that I will take the longest path, which is going this way, then this way, then going down again. And then if I have another thing here, I will go down and up but this doesn't guarantee I can have motion sensor here. So the longest way can have motion sensor. It doesn't guarantee. Okay, let's think for it in a different way. Okay? So it can be more clear. What if I told you? What if I told you? What if I told you is there a bus from S to T while being at least K distance from the center? I've asked you this question. What is the question? Is there a bus from S to T? Is there a bus from the entrance to the mansion junction while being at least K distance away from the sensors? Okay. How can I determine this? First, I need to determine the distance from each junction to the nearest motion sensor, because I don't know. I know only the pipes, the length of the pipe. It's given. Each pipe is with its length, so I know the length for this pipe and the length for this pipe. But what is the shortest path for this junction to a motion sensor? This, or this, or this? I don't know. I need to calculate it. That's right. So that have the shortest path for each junction. So they have the length for each pipe. That's right. The shortest path may be a combination of multiple pipes. That's right. It can be like from this, it can be this and this, or this, or anything. That's right. From this to motion sensor, from this junction to this motion sensor, it can be this, then this. That's right. Or this, then this, then this. Sorry. this than this, or this than this. I need which one? The shortest path out of both. That's right. Okay, so how can I do this? Think about it. How to know if there is a path from S to T while being at least k distance away from the sensors? In order to know whether there is a path or not, what should I do?
You should go through
All of
check-
them?
Yeah, all
Do you remember BFS and DFS? What is the purpose of BFS?
check through your
Traversing the graph.
Yeah.
So what when traversing the graph, I didn't reach the matching junction, it means what? There is no path.
There's no problem.
So checking the path may be implemented using BFS or DFS. Why use for DFS? The complexity for the Dijkstra is E log V, which is here is N log N, because both of them are N. But for BFS is V plus E, which is N plus N, which is N. So the complexity for BFS is smaller, but it cannot get the shortest path. Unlike the Dijkstra, solves the shortest path from a single source, that's right, but traverse slower than BFS. BFS is like suited more for traversal algorithms, or for traversal purposes. Okay? Okay. So what I'm talking about here, how to get a path from S to T while being at least distance from the sensors. What simply the solution is what? The solution simply remove any vertex or any junction with distance less than k from any sensor.
How do you determine that K?
Less than k.
How do you determine it?
What should I do here? I am saying here that I will remove any vertex with distance less than k from any sensor. What's meant by this? What if I told you that I need to be at least k distance away from the sensors? Let's imagine that k is, or let's assume that k is 10. Okay? So what if this is 5? 5 is smaller or greater than 10? Smaller. So I need to remove this vertex because it has a distance smaller than k. I need to have a distance more than k to maximize the probability of being, to minimize the probability of being catched. So I need to maximize the distance. If this is 5, this is 6. So this is valid or not? 5 plus 6 is 11. The shortest path from this to this is 11, and from this to this is much more. So the shortest path for me to any motion sensor is 11, right? Which is more than k. So I will leave this vertex. After leaving some vertices which are greater than this distance, k, and removing the other vertices which have a distance less than k from any sensor, I will have a new graph with many vertices removed. Now, is this graph connected from S to T or not? If connected, then this k is valid and is good. Should I finish or find out a bigger k? Or try to find out a bigger k, because I need to maximize the distance as much as possible. That's right? Okay, so what should I do here? I will make GT equal sub graph of G having vertices with distance so I'm here stating that our new graph is called GK. What is GK? GK is subgraph of G, but having vertices only with distance greater than K to any distance smaller than K, I will remove its junction. Okay? You have a question? What is the question?
How are you able to find K if you don't know where the motion sensor is?
Yeah, how to find K? I will start this. But first, the K is the largest possible value that make the graph reachable from S to T. That's right? Okay. In order to know Okay, let's focus. So what should I do now? How to know if I assume that there is some key. The key is, for example, 10. So I should remove this because it's 5, the rest is 5, and keep this because it's 11, right?
Yeah.
Okay. But how to get the distance itself? How to know the shortest path from this junction to the nearest entry point, to the nearest motion sensor? How to know it?
By finding the distance between.
How to find the shortest path for every sensor from each junction? I need to get the minimum distance from each junction. So I need to get this junction and the shortest path for this with the value and this with the value. If the shortest path with any motion sensor is smaller than 10, it means that it makes sense to me. So I need to maximize it to exceed 10. Did you understand? Okay, so how can I do this? I need first to calculate the distances, that's right. Do I have a distance between the junction and the motion sensor? No, I don't have. I only have the length of the pulse.
Yeah.
But maybe between this vertex and the motion sensor is 1, 2, 3. Maybe it's like, I don't know. So which algorithm gets you the shortest path? Dijkstra. Why? Because this graph is weighted. Do you remember the last lab? We made for the shortest path BFS, if you remember. How? Because he told you that the wire in the network, if you remember, is some constant multiplied by the router, which is 100K. So it's constant. So BFS is much less in complexity than Dijkstra because it's linear, V plus E. Unlike this, which is V, E log V. So the other one is smaller. But what if the weight is unbounded? Here he tells you that the pipe has a length. Did he specify that the length is a constant? Or a constant multiplied by the n? No. So I cannot use it, and I cannot use at all BFS. I should use only Dijkstra because the weights are positive. That's right. Did you got it? Okay. So 2. No. So we need to calculate the distance from each vertex to every sensor. How to make this? How to calculate the distance from each vertex to every sensor? How to make this?
How would you do with the Dijkstra algorithm?
Yeah, I will do a Dijkstra, that's right. But what if I made Dijkstra from here, from this motion sensor? It will get me the shortest path from this motion sensor to all other junctions. So it will tell me that the smallest distance, shortest path between this and this is 70, for example. 70 is good, it's much greater than 10. But is this the nearest motion sensor? Or there exists a one that is much more near, which is this one. So I need to make the Dijkstra from every motion sensor or from every junction. Both are correct. Why? Making the Dijkstra from every junction will tell me the shortest path to every other junction, including the motion sensors. And doing from the motion sensor, he will tell me that the minimum distance from this to this is what? Is 70, for example. When I have another motion sensor, it will tell me it's 5, so I will override the 70 with 5. So now the minimum distance for the nearest, the shortest path for a motion sensor will be 5 instead of 7. That's right? Okay, so here it tells you calculating distance from each motion sensor to each junction requires what? Requires running the Dijkstra. How many times? Requires running the Dijkstra from each junction or from each sensor. And from each sensor will be much more like logical because it's fewer than the junctions, right? But what the complexity here? What will be? Complexity here will be equal to O what? The Dijkstra One Dijkstra costs me n log n. From where did I get n log n? Because it's e log v, and the n, v are both n, so it's n log n. Okay, n log n, very good. I will do this Dijkstra how many times? With each motion sensor. Do I know the count of motion sensors? No. They are like, with respect to the number of junctions, which are n. So it will be also bounded by n. It will be n square log n. And I told you that I need it in only n log n. So what is the solution here? What should I do? Is there a better approach? The problem here is that I need to like execute Dijkstra from each motion sensor or from each node. So executing it only once takes n log n. Multiple times will take n log n by the number of times which is n. So it will be n square log n, which is invalid regarding to complexity. How to solve this?
But if you have removed some nodes via the first instant, well,
Okay, but in order to make you like, in order to ensure that you are understanding what I'm trying to do, what we are trying to do, we are trying to know if we have some key. Is there a path from the entrance to the mansion or not? How to know this? I will remove any key, any junction having a smaller distance than this key. But how to get this distance itself? I need a shortest path algorithm. That's right. Getting this distance requires a shortest path algorithm. That's right. You understand? Okay. So what should I do now? What? How to decrease this complexity? What should I do? The problem here is I need to implement or execute the Dijkstra multiple times. Is there a workaround I can do?
What if you can execute it from one node?
Which node?
The entrance point?
But okay, executing it from the entrance point will give me shortest path from this to the entrance and from this to the entrance. Do I need shortest path to the entrance or to the nearest motion sensor? The next motion sensor, that's right. What will I do with the nearest distance to the entrance? I'm trying not to be detected or captured, so I need to avoid the motion sensor. So I need shortest path to a motion sensor, to any motion sensor, or shortest path to a motion sensor. That's right. So I need to calculate the shortest path from every junction to every motion sensor. So now I have each junction is nearest to which motion sensor, and I will reserve this value for distance. That's right. Okay, but how can I do this? Can I find a single point that I can start from instead of starting from multiple points, so I can do the Dijkstra only once? How can I do this? Think about it. I think bonus if you told it.
What if you
How?
What if you run?
Okay, I'm asking about here. I'm trying to get the shortest path from every junction to the nearest motion sensor. So doing this will require me to run the Dijkstra multiple times with each motion sensor, which is n log n multiplied by the number of motion sensors, which is n square log n.
If you run the Dijkstra from the entrance node to all other nodes, that is you running it once.
Yeah, once, but it doesn't.
But that gives you the motion sensor that is nearest to it.
No, it will get you the shortest path from every junction to the entrance, not to the nearest motion sensor.
But wouldn't it also find to the motion sensor as well? Because the motion sensor is also part of the junction, right?
Yeah, but not every junction. Some junctions only have motion sensor, not all of them. So when I'm getting here,
But if you find it to the nearest
I need the distance here to be stored. This distance or this distance? I need the distance for the motion sensor, not the distance for the entrance. So in order to make the distance for the motion sensor, to store this, I need to run from each motion sensor. From the entrance, it will store it for you. This junction is this length, and this junction is this length.
What I'm trying to say is if you get the first motion sensor, which means you can.
No, I need to avoid all motion sensors, distance, some distance, not the first motion sensor. If I will give you an example. What if I avoided this because it has a near motion sensor? I will go this way. I can find here motion sensor on the junction.
It's like finding the first motion sensor, and then from the first motion sensor you can find any other motion sensors that, and then you run like Dijkstra from that first motion sensor that you.
No, it's not working this way. Not working. Because the Dijkstra get only works from a single source. So you need to determine a specific single source. And it will give you the shortest path from this specific point. Only. Not other points.
Why do you learn it from the machine itself?
From what?
First motion.
I don't. It doesn't matter how far those junctions are from the mansion. What matters is how far from the motion sensor.
How do you get the motion sensor?
Okay, I'll tell you. It's very, very easy. I'll tell you. There are other questions. Don't worry. I will connect all those motion sensors with a new node called X. Okay, focus with me. Now I will run the Dijkstra from which node? From the new node, which is connected to every motion sensor. So now we're getting the shortest distance from X to any other junction to give me what is the distance from those motion sensors to any other junction. But in order to guarantee this, I need to put the weight with what is the weight I select? What is the weight value? I should connect them with what? Something that does not change the result, which is 0 and 0. Okay, again, what did I do here? I connected all the motion sensors with another new node called X. Okay, and the weight between this node and every motion sensor is 0. Why? Now I'm making shortest path from which node? From X. Okay, making from X, it will give me shortest path from X to this, and to this, and to this, and to this, and to every other vertex. And this vertex is directly connected to all motion sensors with distance or with weight 0. So getting from this to this 5 means it's 0 plus 5, because 0 will not differ the answer. So now I have got the shortest distance from any vertex to the nearest motion sensor. Why? Did you understand it? You understand? For sure?
No.
Is it complicated?
Yes.
Why? We need the distance from every junction to the nearest motion sensor, that's right? So how can I do this? Focus with me. If I have something like this, here is the motion sensor. Okay.
The first question.
Getting this distance. How can I get this distance? I need this distance, which is the shortest path for this distance, with respect to whom? The motion sensor, which is this one. If I made the Dijkstra from this, it will give me this is the shortest path. But I'm trying to figure out what is the shortest path from a motion sensor, which is this. What if I have multiple motion sensors? I need to once run it with this one and once run it with this one. Why? Because this will give me a very huge value, but actually I have another near motion sensor which will catch me. That's right. So I need to get the nearest motion sensor from this junction, which is 5, for example. How to get it? I will run only the Dijkstra once, and instead of running from each motion sensor, I will run with a vertex connected to all motion sensors with weight 0. So it's like exactly I'm running it from every motion sensor, because this is connected directly to motion sensors. So instead of running it multiple times, I will run it only one time. You got it?
My question was in the first place.
What?
My question was in the first place. Do we know the number of do we know exactly the number?
Yeah, we know. It's million motion sensors. What should you do? It's very huge. So what should you do? You will try Dijkstra from every one of the million. So there are too many. Instead, you can only connect a node with all those million motion sensors. When you run from this node, it's connected to all other with weight 0. So it's like running from everyone, the same exact result, but only running it once. You got it? Okay, very good. Let's continue.
Will it work in real life?
What?
Will it work in real life?
Yeah.
Okay.
Okay, let's continue. Because we don't have enough time, so let's continue. Did you understand this? Where did this convection come from?
Running it from other node.
Dijkstra from each center of from each junction, doesn't matter, both will lead me n smaller than n. That's right?
Yeah.
Okay. What's the better approach? As you said,
Running from 1 to 0. Let's have
So now-
single source.
so now what will I do? I will make G dash equal what? Equal G with what? With extra
The extra node, of course. It's the extra.
vertex. X connected to
All other vertices.
all sensors. Do you remember you took already a similar concept for this the previous lab? But the super node connected to all entry points, if you remember. Because we had also multiple antennas that we need to run from. Here we have also multiple. So in order to make a single point, I need to connect it with all of them with weight 0. Because if I connect it with weight 5, so there is an additional distance, and I don't want additional weight. So I will connect it with 0 because it will not differ the answer. You got it?
Yeah.
Okay. And towards answer with weight what? With weight. You have any question? So now instead of having G, I will have G dash with this new vertex and this new connections. You have any questions till now? Is it clear?
Yeah.
Okay. Now, what does this denote? In order to make sure that you understood, what does this denote?
That is running from a single
The
source.
shortest path from X to any vertex, the shortest path from a motion sensor to, or in other words, the shortest path from a vertex to the nearest. That's right? You got it? Because which one will update this? I will have another connection here, 5 plus 10 plus 20 plus 50 plus, it will give me 80. But getting here will give me 5. 5 is smaller or 80? 5. So I will keep 5. You got it? Okay. How to solve it? So again, in order to make sure that you understood, again, what is the purpose here? The purpose is to maximize the distance, which is called maximize some k or some distance to the sensors in order to minimize the probability of being captured. That's right? Okay. So how can I do this?
The distance
We assume that if we need to get to know if there's a pass when at least being k distance, what should I do? I will remove any sensor, sorry, I will remove any junction
Any junction
that has a distance less than this key. And I will have a new subgraph which has only the new junctions or only the junctions that doesn't violate the condition. That's right? That have enough distance far from the sensors. Okay. But how to know what's the distance from any junction to the nearest motion sensor? The Dijkstra one time, instead of doing it multiple times. Did you understand till now what we are trying to do? Now we have the distance, so now we can check the reachability from the entrance to the matching junction when using any key value. That's right? Okay, but which key do we need? The largest possible key, not any key, the largest possible one. That's right? Okay, that's very important. So we told you here. We can construct GK from G by removing what?
moving the one by
Any vertex that has a distance from the new node, which is a super node, to any vertex smaller than what?
Okay.
Smaller than k. I will remove it. That's right. Okay, how to check that is it reachable or not? How to check reachability from S to Z. How to check reachability?
If you can still
How to check reachability from S to Z? When removing those nodes having distance smaller than k, how to check reachability?
If it's still
Connected.
They're still connected.
There is a connection from S to T. Whichever result tells you there is a connection.
Yeah.
D plus or B plus. Also the Dijkstra also B plus and D plus is much like has a better complexity, much faster. So I will do this with how to check.
Check trouble us.
Use BFS or complexity. What's the complexity here?
Well then.
It's n. Why n? Because the number of matrices is n and E is n, which is n plus n, which is n. V plus E, that's right?
Yeah.
Is there any problem? Okay, what is the solution? Our solution one, our goal is to find what? Our goal is to find which key? The largest key is that we serve a connection from S to C. So let's denote this. Our goal is to find K star. What is K star? The largest K where GK is connected from source to target. Did you got it?
Yeah.
You got it?
Yeah.
You have any question? Okay, how to get this K star? Can you tell me what are your opinion?
Okay.
How to get this K star? What can I do? I can try one. Did one work? Yeah, I will try two. Did two work? Is there a possible two? Yeah, I will try 3, 4, 5, 6, 7, 10, 11. 11 didn't work, so I will choose 10 because 10 worked and 11 didn't work. So 10 is the largest possible distance that ensures that there is a path from S to T. Did you understand? Why don't I choose 2? Because 2 is smaller than 10 and both of them make that connected, to which is better 10 because it maximizes the distance. Okay, so what is the complexity for such a thing?
I mean, you have to go to A again.
So here we tell you we can find K star simply by constructing GK for every K belongs from what? From 1 to K star plus 1. I will try what? I will try removing all smaller than 1. 2, 3, 4, 5 until which K star plus 1. If K star plus 1 is invalid, so which largest thing is invalid? K star. K star. That's right?
Why if you have K star plus 1?
What if you try 1, it works, 2 works, 10 works, 11 didn't work. So you will finish with 10. So in order to know that 10 is the largest thing, you need to try 11. So here we are looking for K star plus 1. So our logic is K star. What's the complexity of this? What's the complexity? What's the complexity
Well,
of doing this? First we made the Dijkstra, which is
which is n log. Log reduce it to n log n.
n log n. Remember, because we made the Dijkstra only from a single source. So complexity is n log n because of Dijkstra. K plus what?
Plus another k.
Plus, I'm looking till K star. Each time I'm checking for the reachability. With 1 I'm checking the reachability and with 2 I'm checking the reachability. Checking the reachability requires complexity of n. So I will check reachability each time from 1 to K star plus 1, which is K star time. So it will be n, which is for BFS, multiplied by K star. But is this good? He needs a complexity n log n. Is n K star correct? What is K star? Does K star depend on n? No. K star here is
Independent of n.
K star here is unbounded. It doesn't depend on n, so it may be much larger. It may be smaller. I don't know. So this solution cannot work.
Can you just ignore the case now?
Can you think about another solution? Can you think about another solution? Why can't we binary search? We need something log, that's right? We need log. So can we binary search?
Binary search through the whole.
We need the binary search needs a beginning and an end. What is our end? What?
It's not the machine that is our solution, it's that key.
Well, you don't know the key. So what is the end? If you said trillion, maybe the shortest bus more than, maybe you have like some distances larger than trillion. So what is your end?
It's to find the feasible, right? To try to find at what point can we.
Yeah, exactly. So it's saying something good. We need to find the largest visible things, right? What is the largest visible distance? Guys, focus with me. What is the largest visible distance? It's the distance from a motion sensor to the furthest point, that's right? Which meaning like the distance from like this to
Done.
this, right?
Yeah.
This is the furthest point. I'm sure that if I remove this,
Once
I remove all other points.
Yeah, once you
If I remove this junction, if I got this distance, if I took the maximum distance, we already have got the distance from every junction to the nearest entry one, to the nearest sensor. What if I got the maximum out of all of them? I will get the maximum, which is this with this. Sorry, no, not this with this. This with this, no. This with this, maybe with this, or this with this. What if I got maximum is this with this? It means remove any other thing. Do you understand? Again. If I got the maximum thing, what is the maximum shortest bus? The junction from this
to that.
motion sensor. Removing any smaller thing will remove this and remove this and remove this. Remove anything. So what I'm searching for is something in the middle between one and this large maximum, right? Did you understand? Did you get it? Okay, so what should I do? What is solution 2?
So if you do the binary search over there, it will give you
Okay.
the biggest source.
So I told you, let Z bar be the maximum distance from a sensor to a vertex, which means Z bar equal max for every distance from starting node to. We have already calculated this, that's right? So getting the maximum distance from the starting to any vertex will, getting the maximum one of them, I will guarantee that all of them will be, if I remove this, all of them will be also removed because all of their distance is smaller than this maximum distance. Did you get it? Okay, but what should I do here? So I will look from which I will make binary search from 1 till Z dash. From 1 to this maximum, which is called Z dash, that's right? I will get the middle. Okay. What if the middle, what if I check the middle and remove a vertex smaller than the middle distance and it was reachable from SSP? Should I go solve this way or this way? What if this M had a pass from SSP? Should I continue with this half or this half? Right or left? Which is bigger than M, but M works, so I need to find much more larger because I need the maximum distance. So if it's valid, I will go to this half, or conquer on this half. But what if it's invalid? It means this key is very big, that there is no pass from S to C. So I need to search for a big one, but still smaller than this, so I can reach my target, right? So I will search in this, and so on until I reach the largest distance that make it still reachable. What's the complexity for this?
Binary search of course goes to the right.
Complexity is what?
If there's only binary
N log N. which is the Dijkstra again,
Plus log n1.
plus what? Checking the reachability each time is n.
Yes.
Right?
And
So
you
it's
bring in log n time.
O of n,
And log
which is bs. Look what? I'm looking till z
Z.
bar, right? But this is a bar, so it will be log
Z.
bar. But what is z bar?
Z bar. It's definitely, it's the largest distance you have.
What is z bar? Do I know z bar? Is z bar related to n? To the number of junctions? Maybe the number of junctions is only 20 and this z bar is 1 trillion. So log 1 trillion is still large. So also this solution will not hold. Is solution 2. Why? Because z bar is also unbounded. So it means that I need log n, not log z bar. So this is very, very important. Focus on me. This is the last thing. So instead of binary searching from 1 to z bar, I can make something that is much more simple. What can I do? Can you think about it?
So we are trying to look for a bound here. That's what we're trying to look for. Make sure that
What? Quick sort. Why quick sort? It doesn't matter. What will you do after sorting? I will tell you that trick. You have already calculated what? The distance, the shortest distance from each junction to any sensor. So how many senses do you have? This one, that's right, which holds the nearest distance from this junction to the nearest motion sensor. And the distance here refers to the distance from this junction to the nearest motion sensor, which is this or this one. That's right, as we said, because this will be updated because this is smaller than this. That's right. Okay. So why can't I binary search on the array of distances itself? You understand? What I mean by this? First, in order to binary search, I will sort. Sort what? Sort the array of distances. What is the complexity of sorting? How many vertices do I have? Vertex do I have n? Sorting them will be n log n. So it will be n log n with merge sort or quick sort. That's right. This is the first step. What's the second step? Binary search on this array of distances. I will binary search on this array. Okay? Focus with me. I will binary search on this array. Why will I binary search on this array? What if the array consists of this distances like 20, 80, 500, 8,000, 20,000, 45,000, 1 million, 1 trillion, for example. What if the array of distances is like that? What should I do? How to binary search? I will get what? The middle element, which is 200,000, that's right? Getting the middle element, I will check whether it's reachable or not. If I remove any distance smaller than 200,000, will it be reachable or not? If it is unreachable, should I go upward or this way? Up. This will not work. It's not reachable, so I will go to the left. So I will solve this. I will get the middle area. The middle area is 500. When checking 500, it was reachable. So I will go again left. So I will get this middle. Here it was reachable. So what is my answer? This is 8,000. Someone can tell me why shouldn't I try 8,001, 8,010, 100,000? There is many numbers between 8,000 and 100,000. But does those numbers matter? Why? What if I removed any numbers smaller than 8,000 to remove all of these? What if I removed any numbers smaller than 100,000 to remove also all of these? So I don't need to check all of the range between those. Getting binary search on the array of distance itself, I'm sure that those are the distances that exist for the junction. So when getting the biggest valid one, I don't need to check the ones after it. Because the ones after it will remove also the same one that this will. Because anything above this will remove the same set, which is those format will keep those. Did you understand it? What's the complexity here? O of n log n for Dijkstra, that's right? Plus O of n log n for Solar. Plus I check the stability each time. How many times for maximum? I have an array of n. I'm making binary search which is log n. And this time I'm checking stability. I have another n log n. yn which is bfs for checking stability. Log n for binary search on this array. So I have 3n log n which is at the end, and log n which is what is required. You got it? Is it hard in the exam? Or is it good?
Very hard.
No, yeah, don't worry about it. No problems will come like this long, but do you understand the concept behind it?
Yes.
Is it clear? Okay, let's go further with the last one because we have another problem. We have only 20 minutes, so we need to wrap. Do you have any questions for this problem? You understand it or not? Okay. I'm binary searching on the array distance itself.
Instead of searching on the distance.
And I told them, a first example I will tell you it fast. What if I have here some numbers, and here is 8,000, here is 200,000, and other numbers. Get example here will give me this. This makes them any distance less than this, we're removing it, make the graph on each other. So I will go further, up or left, to right or up? Up, which is left, which right? So it will give me this method. This works. So I will go further. It gives me this. Is 8,000 working? Yeah. But the next one is not working. So do I need to check for 8,001 and 8,002 and 100,000? No. Why? Because there is no distance that exists in these values. I'm sure if I choose 8,000 to remove all of those, let's say I remove all of those. What about 100,000? I remove the same because they don't exist except those. So I don't need to check for every range between this and this. Removing any set above this, we remove the same set until this. You got it? You got it for sure? Okay. Let's go further with the second example. I have only 15 minutes and this example is very, very good. So I need to write it fast. Okay, I will ask you a question. Do you need to continue this bar today or the next time? I think the next time is support for the project.
The next for the
Next time is what?
support for the
Because we now have only 15 minutes. So I don't know whether those 15 minutes
It's not going to be. We solved the first question.
No.
in 1 hour.
No, the second is like similar.
I think
Similar to have 15 minutes. So what's your opinion? Should I like
the next class
postpone it for the next? I don't know whether it exists a next lab or not. But I can try to discuss it with you the next lab if you want.
Yes.
But I don't know whether there is a lab or not. So if there, in the worst case, if there is not a lab, we can take this lab the next Sunday, and I can discuss it and also record it because the recording is very important for you to study. Okay, so I will need to I will record it next.
Because we don't want
I will revise the Dijkstra again because I didn't revise the Dijkstra to the end. I will revise the Dijkstra again because it wasn't recorded all of it, and then I will solve the second.
What about the other like smartphone. Are we not studying in the lab?
Maybe I will try to study it for you the next time. Okay? But I need to have contact with one of you so I can discuss it on the next lab. Both can you contact me on Teams or on Messenger, anything? Anything. Also even on WhatsApp if you want. You can contact me in order to arrange with you in the next section to discuss the law. But I don't know whether the next section will have it may have hands-on bonus. So I don't know if it has hands-on with bonus. I can make two arrangements, one with the hands-on and one with this. Okay? You have a problem with this, but it's okay. Okay? For sure?
Yes.